Welcome to the talk Learning Properties in LTL intersected ACTL from positive examples only, based on joint work by my colleagues Daniel and Ivan from the Max Planck Institute for Software Systems and me. In this talk, we will show how to infer properties of reactive systems from positive example traces alone. But let's first of all have a look at what this would be good for. In the engineering process of reactive systems, we need a good understanding of the properties of the environment in which the system is supposed to operate in. Similarly, the properties that the system should itself fulfill also need to be well understood, as otherwise we cannot build correct reactive systems. Properties of the environment refer to which inputs the environment can produce, while properties of the system refer to which input-output behavior the system can exhibit. Input and output of reactive systems come in so-called traces, which are temporal sequences of the input and output of the system over time. Unfortunately, properties over the possible or allowed environment or system traces are not always available. They are frequently considered too hard to formalize, and sometimes they are not even known. This makes the engineering process of reactive systems difficult. How can we build systems that behave correctly in their environments if we do not know how the environment can behave? Similarly, how can we build correct systems if we do not know what correctness means, but if only examples of correct behavior are available? To the rescue comes that quite often we can observe environments. This opens the door to inferring the environment properties from observations. Similarly, we frequently have example black box system implementations whose traces we can observe, but whose implementations are too complex to analyze for which properties they satisfy. What we need is a way to infer properties from traces. This is at a first glance quite similar to the setting of learning automata over finite words from sets of words that the automaton should accept and those that it should not accept. The figure on the left shows an example. When searching for a deterministic automaton over finite words that accepts the word AA but rejects the word AB, the automaton shown is the smallest one that exists. Gold's algorithm can be used to solve this problem. The automaton size is used as a natural measure of generalization of the learned property in this case. Without it, a possible solution would be to learn an automaton accepting precisely the positive examples, which provides no insight. For the setting of learning temporal properties for reactive systems, there are, however, two key differences. First, reactive systems do not terminate. So we need to learn automata over infinite words, such as Buki automata. The given traces can also not be finite, but need to be infinite, and in practice they are normally lasso-shaped, with a lasso handle for the beginning of the word, and a lasso cycle for the part that is repeated infinitely often. Secondly, and probably more importantly, in many applications, we only have positive examples, as depicted here on the right-hand side. For instance, when observing the behavior of environments, we can often not tell that some behavior is impossible for the environment. At a first glance, this makes the learning problem ill-defined. A smallest automaton is always the one accepting all traces, which again provides no insight. So we need to be careful when defining the problem of learning from positive examples alone. We have to avoid trivial solutions and yet define the learning problem in a way that is useful in practical applications. A possibility would be to search for an automaton accepting as few words as possible, but accepting the positive examples. At the same time, we could restrict the number of states to some limit to avoid obtaining an automaton accepting only the positive examples and nothing else. The number of states is used as a parameter to restrict the complexity of the learned language, so that in the absence of negative examples, we can still avoid trivial solutions. An example is given here on the slide. Now, for this example, there are multiple possible different automata with two states, and they are incomparable. This is problematic, because now we do not know which one is the correct one for the environment. This is unsatisfactory, both from theoretical and practical points of view. Solutions to learning problems should be unique whenever possible. And, from a practical point of view, asking the specification engineer to select the right language from a set of possibilities is not exactly nice. So we asked ourselves, Is there a way to learn languages from positive examples alone such that A. We use some natural complexity criterion for the learned language, B. It works with omega regular properties, and C. The solution is unique? And what we found was that the answer is yes, if we restrict our attention to those properties contained in a class known under the name ACTL intersected LTL. Let us have a quick recap on LTL and CTL, as we will need this to discuss the class ACTL intersected LTL. Linear temporal logic talks about individual execution traces. For example, globally finally x states that globally, for every point in time, it is the case that at some point in the future, meaning finally, the variable x will have a true value. This is the same as saying that infinitely often x is true. But there's also computation tree logic, abbreviated as CTL. As its name suggests, it talks about computation trees. CTL uses operators that are similar to those in LTL, but it also has two quantifiers over tree branches. E stands for there exists, and A stands for all branches. For example, the formula exists finally always globally x tells that there is a branch on which eventually in the future a point is reached, from which x holds all of the time from all traces from there. If we assume that from this node onwards x is always true, then always globally x holds from there. And then the whole CTL formula holds because there exists this path from the root of the tree to the blue subtree. If a CTL formula uses only universal path quantifiers, meaning only A's and no E's, then it is said to be in the logic ACTL. Now, we said that we consider properties in ACTL intersected LTL. If the specification can be formalized in CTL without the existential operator E, then it is in ACTL, as just stated. If the specification can also be checked by testing all traces of the system against a fixed LTL property, then the specification can be expressed in LTL. If it can be expressed in either way, then it is in ACTL intersected LTL. The figure here on the slide depicts that there are some properties that are representable only in ACTL, such as always finally always globally x, and there are some that can only be represented in LTL, such as finally globally x. But there are also some that are representable in either ACTL or LTL, such as the one here in the middle. We can either check if a computation fulfills always globally always eventually A, or we can check if each trace in a computation tree fulfills globally finally A. The result will be the same in both cases. Many specifications commonly found in practical model checking fall into the ACTL intersected LTL class, which makes it interesting. For instance, the work by Blahudek et al. Included a collection of LTL properties used in model checking. Out of the 134 unique LTL properties in that work, 77 are in this class. And most non-representable cases are of the form finally globally something, and whose complement is then again in the class ACTL intersected LTL. But what is even more interesting, Monika Meidel identified a class of automata called universal very weak automata as characterizing the class of properties in ACTL intersected LTL. And our focus on this class is built on the properties of these automata. Universal very weak automata are also abbreviated as UVW. And to provide some intuition on how a UVW works, we introduce them by example. Universal very weak automata accept infinite words for which all runs for the word do not visit rejecting states infinitely often. These rejecting states are depicted doubly circled. Take for example the automaton depicted on this slide, which corresponds to the LTL property globally A weak until B until C. There are three ways by which this formula can be violated, and since for universal automata a word is only accepted if all automaton runs are accepting, these three ways are encoded by the three paths through the automaton. First of all, if at some point during a trace a character is seen for which neither A nor B nor C hold, then A weak until B until C cannot be satisfied from that character onwards. This is implemented by the initial state self-looping, so that there's always a run of the automaton staying there long enough, and then transitioning under such a character witnessing the violation to a state rejecting all suffix words. Then, if there are only finitely many C's in the word, then there is a run eventually visiting Q2 and never leaving it again. Since Q2 is rejecting, the run is also rejecting. Finally, if at some point of a trace no C is seen, so that A weak until B needs to hold from the trace element for the trace to satisfy the LTL property, and there is no B seen at the same time, then it needs to be checked if A weak until B holds from there. The state Q1 is responsible for this check, and there exists a rejecting suffix run from that state if and only if A weak until B does not hold. So let's see what the properties of universal very weak automata are. The term very weak in their name refers to the fact that all loops in these automata are self-loops, so that it has the structure of a directed acyclic graph with additional self-loops at some states. A path in this graph is also called a simple chain, and we have seen that the LTL property on this slide can be decomposed into 3 such paths, all representing individual ways in which the property can be violated. Simple properties tend to be representable by UVWs in which the chains are short, whereas for more complex properties, longer chains are needed. This observation gives rise to a problem definition for learning UVWs from positive examples alone. Given a set of positive examples and a maximal chain length, we want to compute the strongest UVW accepting the positive examples and whose chains are not longer than this maximal length. The contributions of this work are now the following. First, we prove that for every set of possible examples, the language that the learned UVW needs to have using this problem definition is unique. Hence, it actually fixes the drawback of earlier learning approaches from positive examples alone that multiple incomparable languages could be learned. Then, we provide a learning algorithm for solving exactly this learning problem. The learning algorithm makes use of the special structure of UVWs. And finally, we evaluate the algorithm on a case study. In the case study, the algorithm always converges to the correct solution if enough positive examples are available, and it can be seen that it's doing so quite efficiently. Let us start with the first contribution. An important aspect of learning UVWs with restricted length of the simple chains is that the strongest such UVW is unique. The paper has a formal proof, but the intuition of the proof is also used in the algorithm for learning UVWs to follow. So let us have a look at why strongest UVWs are unique. Since every loop in a UVW is a self-loop, every UVW can be decomposed into a set of simple chains. A chain is characterized by the self-loop labels and the labels of the transitions between the states. Without loss of generality, we can assume that in every chain exactly the first state is initial and exactly the last state is rejecting. For a given maximal chain length, there are only finitely many different chains. And by this decomposition idea, an automaton consists of a finite set of simple chains. It follows that we can compute a strongest automaton by enumerating all simple chains that are consistent with the positive examples. Taking all these chains together gives us the strongest UVW. We say that a chain is consistent with the positive examples if it does not reject any of the examples. The basic idea of a more efficient learning algorithm that we present in this work is that it suffices to enumerate the strongest chains that are consistent with a given set of positive examples. A UVW that consists only of these strongest chains is language equivalent to a UVW consisting of all possible chains that are consistent with a given set of examples. The example on the slide shows what we mean by a strongest chain. The chain below extends the chain above by each of the character sets in the transition labels below being supersets of the respective character sets in the transition labels of the chain above. This means that every trace rejected by the chain above is also rejected by the chain below. We represent a chain by its chain string. As shown in the image, each position in the string stands for an edge label. alternating between self-loops and edges between states. The partial order between chain strings is an element-wise subset relation. Now that we know how to represent chains by chain strings and defined a partial order over them, we will use this encoding to find all strongest chains. The function f is applied to a chain string s and returns 1 whenever a UVW represented by s rejects any of the positive examples. Note that f is easy to implement. For each positive example, we check if the example is accepted by the chain. This is essentially building the product between the lasso-shaped example and the chain and checking if a rejecting state can be visited infinitely often in the product. How to do this is known from classical state-based model checking. A useful property of this function f is that it is monotone. If it returns 1 for some chain string, then for every strictly stronger chain it also returns 1. For a monotonous function, there's an off-the-shelf algorithm to enumerate the strongest function domain elements that are not mapped to 1 by the function. This is also called the cooperator front of this function, which is exactly what we need. In this way, instead of enumerating all possible simple chains that are consistent with the positive examples, we only go over the cooperator front of the function f and add those chains one by one to the resulting automaton. After each addition, we perform a minimization step in order to keep the resulting automaton small. Finally, let us formalize the properties of this algorithm as a correctness result. The UVW computed as the intersection of all simple chains of a given length consistent with the examples is the unique strongest UVW for that chain length. Removing weaker chains, or rather not considering them in the first place, does not affect the language of the automaton. To get an intuition on how learning UVWs from positive examples only works in practice, we performed an experimental evaluation on some practically relevant properties. For this, we implemented our approach in a tool written in C++ and Python. As a benchmark, we chose learning allowed environment behaviors, as that is a case study known from the field of reactive synthesis, where a finite state system is automatically synthesized from a specification. Applying reactive synthesis requires a formalization of the environment behavior in which the system to synthesize works in. The AHB Bus Protocol is a classical benchmark in reactive synthesis. In a work by Gotthal, Chatterjee, and Hensinger, they formalized 10 environment assumptions that the system to synthesize can assume to hold. We wanted to see if they can be automatically inferred from positive example traces. The properties involve comparisons of discrete signal values against constants, and we abstracted from such details by replacing them by fresh atomic propositions. This table shows the 10 properties written in LTL. While some are rather simple, others are a bit more complex, and hence we have some variety here. Analyzing these 10 properties, we noticed that all of them can be captured by relatively small UVWs. All but property 3 can be described by a UVW of a maximum chain length of 2. After fixing the properties that should be inferred, we needed some positive example traces. We generated 50,000 different words of the form u v to the power of omega for some substrings u and v. We chose the length of u to be 0, 1, 2, 3, or 4 uniformly at random, and also the length of v to be 1, 2, 3, 4, or 5 uniformly at random. We also chose the characters that contain the information which propositions have true or false values at each step uniformly at random. If a generated word was a model for the formula, it was kept. Otherwise, it was discarded and another word was computed. The process was repeated for each property until 50,000 words have been found. Let us first have a look at the behavior of the learning algorithm on property 3, as it provides some intuition on how well the algorithm works. We ran our experiments with maximum chain lengths of 3, which are the red lines, and maximum chain lengths of 2, which are the blue lines. Details on the computer used for the experiments can be found in the paper. We used a timeout of 1 hour for all experiments. At the top of the figure, you can see the number of UVW states for different numbers of positive examples. The full 50,000 generated positive examples are only used for the data points at the very right of this figure. And for all other data points, learning was done with fewer examples. It can be seen that for a chain length of 2, the computed automaton is always small, while for a chain length of 3, the computed UVW can be quite large if not enough examples are available. This happens here at the beginning. Otherwise, the resulting automaton is also very small. This is actually a property of the problem that our learning algorithm solves. If only few positive examples are given, the strictest UVW contains chains that would be ruled out by additional positive examples. The computation time in seconds is given in the lower half of the figure. If the automaton computed is large, then also the computation time is long. Otherwise, the computation time is quite short. It grows a bit with the number of positive examples given, which makes sense since all positive examples are checked against the candidate chains during the enumeration process of the strongest chains. The UVW learned for the chain length of 3 looks like this. It can be seen that there are 2 chains from the initial state to the rejecting state Q3, representing the ways in which the property can be violated. There's one chain for each of the possible values that the variable b can have in a character. The states Q1 and Q2 then check that if the value changes to the next step, the value of a cannot be false. Whenever that is not the case, the state Q3 is reached. The self loop in the final state makes sure that once the property is violated, the property cannot be satisfied by a suffix word anymore. Now finally, let us have a look at which UVW is computed for the case of a chain length of only 2, which is not enough for this LTL property. Interestingly, the learned property is a liveness property. It over-approximates the property to be learned and only rejects words on which the character at which the violation becomes apparent is repeated forever. In a sense, the edge label here is moved to the self loop right here. We can see that the learned property still somewhat makes sense, but of course it's not the right one. We also tried the approach for chain length of 2 and 3 on the other 9 properties. For all of them, a correct UVW was found. That is, one that matches the language of the formula and also has a minimal number of states. Timeouts occurred only when not enough positive examples are given to the algorithm. And for property number 1, also when a chain length of 3 was chosen, even though the property only needed a chain length of 2. The graphs show the relationship of the number of states of the computed UVW and the number of positive examples. In case of timeouts, the graph has a gap for the respective number of positive examples. The behavior that we have seen for property number 3 on the previous slide is actually quite typical. If not enough positive examples are available, the computed UVWs are too large. Overall, the experiments show that the approach works and finds the correct UVW, but due to the choice to compute the strictest automaton that is consistent with the positive examples, many positive examples are needed in order to compute the right automaton. To conclude, we presented an approach to learning universal very weak automata from positive examples alone. The approach targets those languages that are in the intersection of ACTL and LTL. The approach guarantees that the solution is unique, and the solution complexity criterion used to make learning from positive examples alone work is quite natural. The learning algorithm is applicable whenever there's a way to compute a good number of lasso-shaped example traces. Our attention to lasso-shaped words was rooted in the fact that we wanted to compute properties over infinite traces. Hence, the example traces also needed to be infinite. When, for example, the traces come from the simulation of a hard-to-analyze system, it is easy to detect that the system state is the same as before, and hence a lasso cycle is closed. However, our approach is also applicable when only finite traces are available. Only safety properties can be learned then, and it is easy to restrict our approach to safety properties by appending lasso cycles with a dummy letter to the positive examples. For full generality, we however focused on general ACTL intersected LTL in this work. The main challenge that has not been addressed in this work is how to pick the correct value for the maximal chain length in a UVW. While many properties of practical relevance have a small maximum chain length, it is not trivial to see from a learned automaton if it has been learned with the correct chain length. Thanks for listening to this talk. We will be happy to take questions during the live session at FMCAT 2020, and in case you're watching this talk at a later time, you can always drop us an email after the conference or open an issue on GitHub regarding the implementation.